Today we're going to take a look at approximation algorithms for MaxSat, so maximum satisfiability. And the focus will be on an approximation algorithm based on randomized rounding. So this is based on linear programming. So you ideally know about linear programming, also interlinear programming. Otherwise, watch those videos first. Let's jump into maximum satisfiability. You most likely know satisfiability, where we have Boolean variables and we have clauses and we want to satisfy the clauses. In maximum satisfiability, we want to satisfy as many clauses as possible, although we don't do as many as possible, but each of the clauses will come with a weight, and then we want to find an assignment of the variables such that the total weight of the clauses that are satisfied is maximized. Total weight meaning sum of weights. In MaxSat, just as in satisfiability, we have literals, so that is a variable or its negation. Clauses consist of disjunctions of literals, and the length of a clause is the number of literals in that clause. And this obviously is an NP-hard problem, since satisfiability as such is NP. Let's take a look at an example of a Boolean formula. So here we have a Boolean formula in conjunctive normal form. Is it satisfiable? Yes, it is. For instance, by setting x1 to true, x2 to true, then all three of the clauses are satisfied, and x3 and x4 actually don't matter anymore. Now, before coming to randomized rounding, we will first take a look at a very simple randomized algorithm. And this algorithm simply does the following. Each variable we set to true, or we will say call it here 1, with probability 1/2, and otherwise we set it to 0, false. And this extremely simple algorithm gives us an expected 1/2 approximation. So if we take a look at the expected value of the solution of this algorithm, that is at most a factor 1/2 away from the optimal solution. And for the analysis, we're going to use these variables, random variables yi, which correspond to the true value of the clause of Cj. So in particular, yi with probability 1/2, or yj with probability 1/2 is 1, with probability 1/2 is 0. And now w is the weight of the satisfied clauses, and I can express w in terms of the yj and the weights for the clauses. So what we need to prove, or what the theorem states, is that the expected value for w is at least opt-half, because then we have this 1/2 approximation. So let's take a closer look at this expected value. So we can express w in terms of the yj, namely we get the sum of w, small wj times yj. By linearity of expectation, I can now rewrite it as the sum of yj and then the expected values for the yj. And now, because the yj are 0, 1 variables, so if you calculate the expected value of a 0, 1 variable, then, in general, discrete random variables, you would compute the expectation as a sum x and then x times probability that the variable is x, and x is 0 for anything except for 0 and 1. The factor x, if I have a 0, makes also the summand being 0. So I really just get the probability of yj being 1 here as the value for the expected value, and that's what we're using here. So I get the sum of wj times the probability that cj is satisfied. So now we want to put in something concrete for the probability that cj is satisfied. For that, we need to know the length of cj, so the number of literals in that clause. So if we have that, how large is the probability that cj is satisfied? So we calculate that by looking at what is the probability that it's not satisfied. To make sure, if you want to make sure that it's not, or the only way that it's not satisfied is that for all of the literals, they all don't satisfy that clause. This happens with a probability of 1/2 to the Lj. So this probability is 1 minus 1/2 to the Lj, because exactly 1 out of 2 to the Lj possibilities of assigning the variables does not satisfy the clause. And then Lj is at least 1, and therefore this probability is at least 1/2. But now if each of these probabilities is at least 1/2, then I know that the expected value for W is at least 1/2 times this sum here. And here I have the sum of all weights. And this is obviously an upper bound on opt, because this is what I would get if all clauses are satisfied. Therefore, I have here a bound of opt half. And this is what we wanted to show. This is a randomized algorithm, but it's actually very easy to de-randomize. So what does de-randomize mean? De-randomize is simply a systematic way of taking a randomized algorithm and making it a deterministic algorithm. So our new theorem here will be that we can de-randomize the algorithm, thus we get a deterministic 1/2 approximation of MaxSat. And we're going to de-randomize by the technique of conditional expectations. So conditional expectation, what is that? So the expected value of x conditioned under y is equal to small y is simply, and this is now like a normal expected value, so I have the sum of all x times x of x times the probability that x is x, but now conditioned under y is y. So now I have here conditional probabilities. Those I can write in the following form. So I get the sum of the x and then probability of x is x and y is y divided by the probability that y is y. And now the idea here is that we simply incrementally, so we go through the variables one by one and set them in such a way as to maximize the conditional expectation. Let's take a look at that in detail. So let's prove this theorem. So we're going to first set x1, and for now we keep x2 to xn random. And then later we will also de-randomize those. But for now, let's focus on x1. And we're going to set x1 to 1 exactly if the expected value of w conditioned under x1 is 1 is larger or equal the expected value of w conditioned under x1 is 0. And those are the only two possible values for x1. So depending on which one is larger, or in this case and also larger or equal, I'm going to make that choice. So if this one is larger, then I'm going to set x1 to 0. So there are two questions that we will need to address here. First of all, how do we calculate these conditional expectations? Because if the algorithm wants to make decisions on those conditional expectations, we have to be able to compute them efficiently. And then we should see why this still gives us a 1/2 approximation. But let's first take a look at how to efficiently compute these values. So let's look at the expected value of w, which we know is the following: sum of small wj times the probability that cj is satisfied. And we can see this as a polynomial in P1 to Pn. So on the next slide, I will also give you a different interpretation or a different way of analyzing this, but I find this one actually most intuitive. So I can see this as a polynomial in P1 to Pn, where Pi is the probability that xi is 1. So this is slightly confusing because we know that the probability of xi being 1, because we have our random algorithm, is simply 1/2. But let's assume we allow ourselves to set these probabilities to Pi, and then this probability that Cj is satisfied for any of the Cj is obviously a function of these PIs. But if we have this function and we can easily write it down, then EW conditioned under x1 is 1 is simply, we can simply take that polynomial, set all of the PIs to 1/2. That corresponds to simply picking at random with probability 1/2 one and with probability 1/2 the other one, which corresponds to here x2 to xn being chosen randomly. And we set x1 to 1, meaning with probability 1 we're simply setting x1 to 1, which we have. So in this way we can compute this expectation. Same we can do with x1 being 0, and then we simply will pick the larger one as the one we are going to continue with. Different way of looking at this is the following. So we want to compute this expectations. So this is how we did it so far. If you consider the setting where we already have set some of the variables either to 0 or 1, so false or true, and we consider the clause Cj. Now, if Cj is already satisfied by this choice, ignoring what xi plus 1 to xn is, then Cj simply contributes Wj, and there's nothing to be done about Cj. So the probability that Cj is satisfied is simply 1. If this is not the case, so if none of these so far satisfied Cj, then the probability that by the remaining variables Cj is going to be satisfied is simply 1 minus 1/2 to the k. The k is the number of unassigned variables that show up in Cj. And then the contribution of Cj to the sum is Wj, this value. And what I can conclude again from this is that these conditional probabilities that I will need to set the variables, I can all compute those efficiently. So we know that we can compute the conditional probability, so we can make this choice. Now let's see why this gives us still a 1/2 approximation. So E of W, so the expected value of W, is actually the average between EW of x1 is 0 plus EW of x1 is 1. So this can be easily seen because x1 in the randomized algorithm is simply 0 with probability 1/2 and 1 with probability also 1/2. Therefore, EW is 1/2 times this plus 1/2 times that over here. And what that means, so EW is the average of those two. By the choice of x1 as we do it, so no matter whether we set it to 1 or to 0, we're going to pick the larger of the two. And the larger of the two is of course larger than the average of the two, which corresponds to EW. And therefore, because this is what we would have gotten from the randomized algorithm, and there we already had that this is at least opt/2, we now know that by setting x1 like this, we still stay above opt/2. And now we can continue with x2 and so on. And there we can now simply apply induction. The base case we have already handled. So now let's assume we already have set the first I variables. We want to set the I plus first variable. So we already know that the expected value under setting the first I variables as the algorithm sets them is at least opt/2. Now, similar to what we've seen in the base case, if you now look at this sum here, so here we've set the I plus first one to 0. Here we have set the I plus first one to 1. Divide that by 2. And just as in the base case, this is actually the same as the expected value under setting the first I variables, which by induction hypothesis we now know that that is at least opt/2. So by here picking the larger of those two, we make sure that we get something that is larger equal this value, so larger equal opt/2. So now, starting from a simple randomized algorithm, we got a deterministic algorithm that gives us a 1/2 approximation for max MaxSat. To wrap up this part of the video, let me briefly summarize the derandomization approach that we've seen. So derandomization by conditional expectation. So what we needed was that we could compute conditional probabilities that we would get by setting the variables, and then the algorithm simply in every step did the choice that for that step gave us a better conditional probability, and in that way we were able to guarantee a quality that is at least as good as the expected value. But all of these decisions, so we're doing this step by step, so this is, you could say, a local decision. Now we want to do something more global, and for that we're going to see randomized rounding. So for randomized rounding, we first need to formulate MaxSat, so maximum satisfiability, as an integer linear program, so an ILP. We want to maximize the sum of the weights of the satisfied clauses, and we do so by appropriately setting the variables of our MaxSat problem. So we will have a variable in a linear program for each of the variables of the MaxSat problem, and we will call those variables yi for the variable xi of my satisfiability problem. To express our objective function, we will also want to have variables for the clauses. So we have one variable per clause, and we'll call those zj. And with those variables, so this variable will express that the clause is actually satisfied. So then the objective function is simply maximize wj times zj. And this now is subject to the constraints that the set j are actually allowed to be 1, in the sense that there is actually a variable in that clause that satisfied it if I set j to 1, and we can achieve that in the following way. So we're going to take the sum. So pj is the set of variables that positively occur in clause cj. So, and I will going to take the corresponding yi here, and for those that occur negatively, I'm going to take 1 minus yi. Now, if at least one of the variables that occurs positively is set to true, so if I have at least a 1 here, then I'm allowed to set j to 1. But also if one of the negative ones, at least one of them, is set to false, so then it also satisfies the clause. So if either of these conditions hold, then I'm allowed to set j to 1, and I can express this here by saying that this here is larger equal set j, because what's now happening is if none of these satisfy set j, then they are all 0, then I have to set j to 0. If at least one satisfies them, then the sum is 1 or larger, and then because of our maximization, I will set j to 1, and I can also not set it to more, because set j is constrained to be either 0 or 1. Yeah, so those are my constraints. And now I'm going to relax this integer linear program to get a linear program. So this is the LP relaxation for the integer linear program. And now we're going to use randomized rounding. So we started with an integer linear program, we relaxed it, now we have a linear program. We will solve that, get an optimal solution. And from that optimal solution, now I want to get back a problem for the integer linear program. We do this by appropriately rounding, and the appropriate rounding will happen as follows. So I'm going to take an optimal solution for the relaxed linear program, and now independently I'm going to set xi to 1 with the probability. So I'm going to set xi to 1 with the probability of yi star. This is yi in my optimal solution. So for instance, if yi star is 1, then definitely I want to set i to 1. And this then obviously also happens because it was probability 1 I'm going to do that. But if xy star is 0, I wouldn't want to set xy to 1, and I won't. But if it's in between, now I'm going to do it with the corresponding probability, and we're going to see in a moment why this works so nicely. This provides approximation with the following factor, and this factor you're going to see where that comes from in the analysis. So it's not directly obvious right now here, but the factor is 1 minus 1 divided by e. So this is roughly 0.63, so this is better than the 0.5 that we've seen, and later on we're actually going to see how to combine all of what we've seen so far to get an even better approximation factor of 0.75. To prove all of this, we need a few basic mathematical tools. So let's do this. I'm considering a concave function over 0, 1. Concave, so if it's doubly differentiable, this means that the second derivative is smaller or equal to 0. So graphically, it looks like this. Now, if I have a concave function, then what I have for any value in between 0 and 1, so if the value here is a and the value up there is a plus b, so in particular in between here, this is the difference is b, then for all values in between, if I compare the value that I would get by taking the line through a and b in between, then the f of x is always larger equal that value. Yeah, it's larger equal bx plus a. And now, of course, we started here at 0 and entered a 1 for everything between 0 and 1. Now, the interpretation here is f stays above the line between the two endpoints that I picked. Second tool that I need, so-called arithmetic geometric mean inequality. Sounds fancy, is not that complicated. If I have non-negative numbers, then the geometric mean is smaller or equal to the arithmetic mean. Arithmetic mean, we all know, it's simply the average over all elements. Average that we get by summing them up, dividing by the number of elements. Geometric mean we instead take the product and then the kth root. And this is smaller or equal to the arithmetic mean. Now we are ready to do the analysis of the algorithm using randomized rounding. So let's consider a clause Cj, and let's say it has length Lj. Let's first consider the probability that the clause is not satisfied. So it is not satisfied if everything that occurs positively is set to 0 and everything that occurs negatively is set to 1. So what is a probability that a variable that occurs positively is set to 0? This is simply for each of the variables. The probability that I set it to 1 is yi star. The probability that I set it to 0 therefore is 1 minus yi star. So for each of the variables that occur positively, I get 1 minus yi star. And because I'm interested in the event that all of this happens at once and they're independent, I get this product and additionally the product for the variables that occur negatively. And there I get the yi star simply, so not more and minus, because here I have a problem if it's set to 1, and setting it to 1 happens with this probability of yi star. Now here I have a big product, so not surprisingly, since we already know which tools we want to apply, now we're using the arithmetic mean as an upper bound. So instead of this product, I get this sum. But of course, there was also the kth root and the 1 divided by k. And k here is Lj, so the number of summons, or this number of factors is Lj. So I will have 1 divided by Lj here. And so in the inequality, I have 1 divided by Li up here. I don't actually have it here. So if I do to the Li here, this cancels out, but this gives me the Li here, which I already had shown over here. In the next step, I'm rewriting this to make this look more like the constraints that we had in an integer linear program or linear program, and therefore I'm essentially taking 1 out of here. I now get 1 minus this here. So this equality you can, I would say, most easily see by bringing this 1 back and the minus back into here. So the minus here gives me a minus here, and let's multiply this as minus 1, so I get yi star minus 1, and then bringing in the 1 here gives me a 1 everywhere here and cancels out that one, and then I'm back to this here. And the reason I did this is because this now is exactly the constraint in my linear program. And by that constraint, so since I know that I have a feasible solution to the relaxed problem, I know that this now is larger equal zj star, meaning that I now have the following bound on the probability that Cj is not satisfied. So this now just depends on Zj star and the Lj. Now we're going to look at the probability that Cj is actually satisfied. So this is 1 minus this probability. I can now bound this by this f Zj star. So this was what we just calculated, and now because I'm interested in the probability that Cj is satisfied, I get 1 minus that as a bound. So the probability that Cj is satisfied is larger equal fzj star. And this is now a concave function which I use to bound fzj star by these two extreme values. So f1 times zj star plus f0. Now f0 is simply 0, that cancels out. And f1 is this with a 1 here. So this gives me the bound here that you see here. And now I'm going to make use of the following very often very useful inequality, namely that 1 plus x is smaller equal e to the x. So let me draw this here. This is 1 plus x, so simply a line of slope 1 through 1 through 0, 1, and e of x looks somewhat like this. So it should have been tangent here. So this is a very useful inequality, and I'm going to use this here with x being, x is my 1, I minus 1 divided by aj. So plugging that in, I can now bound this by, so can bound this term here by e to the minus 1 divided by aj, but because I have the lj here, this cancels out with that aj. So I have here 1 minus 1 divided by e as a lower bound times zj star. So we have the probability that Cj is satisfied is at least this number here. And now I can use linearity in the following way. So I get that the expected weight of what the algorithm gives me is the weight, sum over the weight of the clauses, each time multiplied to the probability that that clause is actually satisfied. This I can now bound by 1 minus 1 divided by e times zj star, this probability. So taking the 1 divided by 1 minus 1 divided by e out of the sum, I have now here the sum times that factor. But that sum is simply the objective function of LP. So this is then equal to 1 minus 1 divided by e times the opt of the relaxed LP, which is an upper bound for the integer linear program. So we get here that the expected value of w is larger or equal to 1 minus 1 divided by e times opt, which proves the approximation factor that we wanted to prove. This concludes the proof of the approximation factor of this algorithm. In the final part of the video, we're going to see how to combine both algorithms to get an even better approximation factor. Yeah, so, and the combination is very simple. We're just going to run both algorithms and take the one that gives us a better solution. And this will give us a 3/4 approximation. We prove this by a probabilistic argument. So what we're going to do is we assume that we're not actually taking the better algorithm, but we simply take with probability 1/2 the result from one algorithm and with probability 1/2 the probability of the other algorithm. So this is worse than what we're actually doing if we take the better one. So if I can prove the theorem for this weaker algorithm, then it holds also for the actual algorithm. Yeah, so the better solution is at least as good as what we get from this approach by taking each of them with probability 1/2. For this randomized setting, we're now going to analyze the probability that a clause is satisfied. And this depends on which of the algorithms we picked. And we pick one with a probability 1/2 and the other one also with probability 1/2. So the probability that the clause is satisfied is with probability 1/2, and then the probability or the bound that we got for the LP rounding, and with probability 1/2 the bound that we get from the simple randomized algorithm. So this is the bound we have. We're now going to make it even weaker by multiplying the second part here also by Zj star. Zj star is smaller or equal 1. So by multiplying this in this way, I'm making the probability only smaller. But now I can take the Zj star outside because both of them had it. And I'm going to prove that this expression is larger or equal 3/4 Zj star. And for that, we simply now need to prove that this expression in here is at least 3/4. If we can prove this, then the rest follows from simply linearity. To prove this, we do a case distinction. So what we have here only depends on Lj. We're first going to look at Lj is 1. So if Lj is 1, I have a 1 here. So this is 0, so I have 1 here. If I have a 1 here, so this is 1/2. So here I have 1/2, so I have 1 plus 1/2 divided by 2. This is exactly 3/4. Likewise, for Lj is 2, we again get that this expression is exactly 3/4. So here we would have 1 minus 1/2, so that's 1/2 to the 2 is 1/4, so we have 1 minus that, so we have 3/4 here. Also here we get 3/4, 3/4 plus 3/4 divided by 2 is exactly 3/4. Then for Lj larger or equal 3, we know that this term here is, so that we've already had proven, is larger equal 1 minus 1 divided by e. But likewise, I know that this term here is at least as large as what I get when I plug in 3 here, because the larger the number that I plug in, the larger this becomes. But if I plug in 3, I get 7/8. And now if I add these two up and divide them by 2, then I get something which is roughly 0.753, which is more than 3/4. So this proves this approximation factor of 0.75. Let's also look at this in a picture. So the lower bounds that we had for the two algorithms for the probability that a certain clause was satisfied. So for the simple algorithm, we got this lower bound roughly. So this increases. It gets better the more literals the clause has. And for the randomized rounding, this bound here, this bound looks roughly like that. So there, this gets worse if I have many variables or many literals in the clause. So what we see is that the randomized algorithm is actually better for a larger number of literals in a clause, while the randomized LP rounding is better for a small value of Lj, of the number of literals. So the algorithm takes the better of the two In the analysis, we used the combination of the two algorithms and therefore got here in this picture as the probability, the mean of those two probabilities. And this mean looks like this green curve. And what you actually see that, between 1 and 0, this is below 0.75, but we're only interested in integer values, so we don't care. But therefore also in the analysis, we had to do this case distinction where we did 1 and 2 separately, and then we're able to use a more analytic bound. Yeah, so the mean here always stays above 3/4 for integer values of Lj. And the maximum is at least as good, and this is what the algorithm does. And again, we can de-randomize that algorithm if we want to using conditional expectations. To sum up, what have we seen? So we've seen 2 plus 1 algorithm. Simple randomized algorithm gave us an expected 1/2 approximation. Randomized LP rounding gave us something slightly better, and the combination even gave us this 0.75. All of this can be de-randomized using conditional expectations. We should ask ourselves, can we do better? So how well we can do is still an open problem, but we can indeed do better. So the best known approximation algorithm gives us an approximation factor of 0.796. There are also lower bounds in terms of how well this problem can be approximated. And there, the best known lower bound is 7/8 plus epsilon, and that already holds for the special case of max exactly 3 sat. Every clause contains exactly 3 different literals, which in particular means that for this special case, so not in general, but for the special case, the simple randomized algorithm is actually already optimal, because that one actually there gives us exactly the 7/8. That's all for today. Most importantly, we've seen randomized LP rounding as a very powerful tool in our toolbox for our approximation algorithms.